Okay, this is Paul Geyer, and I will be the presenter today for this PDH source webinar and introduction to fire protection engineering for buildings. I want to place a little emphasis on one or two words in that title, specifically an introduction to. Because that's what this is. This is an introduction to fire protection engineering. This is not a webinar that has been put together targeted at engineers that have been dealing with fire protection issues in building design for many years and are looking for a real nitty-gritty technical discussion. That's not what this is. This webinar is targeted at the entire building design team and those who have a little awareness that there can be and often are fire protection issues in building design. And that's about the extent of your involvement with fire protection to this point in time. That's who this is targeted at. So I hope that's about what you were looking for when you signed up for this. So the way things proceed here with the webinar, I move forward with the discussion for 50 minutes, then we take a 10-minute break so people can check their emails, et cetera, come back, do another 50 minutes, 10 minutes, keep going through that cycle. Now, this is just a 2 PDH and therefore 2-hour webinar, so we'll just go through that cycle 2 times. And this is, of course, an interactive webinar, and questions and comments are welcome and encouraged. And we have 2 mechanisms for communicating. One is the just the audio stream. You can just speak right up with your question or comment. And the other mechanism is the little chat box in the lower right-hand corner of your screen. Occasionally, we may have audio difficulties, feedback, echoes, that sort of thing, in which case I might have to mute one or more of your audio streams, in which case that person or persons would just have the chat box to communicate with. But the chat box works pretty well. And also, right now, everything sounds fine. We have a small group, and my guess would be that we won't have any audio problems. Okay, don't forget you need to take a quiz for this webinar in order to get your registration board credit, and to figure out what you need to do there, you need to go to the PDH source website, log into your account, follow the instructions, and take the quiz. Also, you may possibly want to have a copy of these PowerPoints that we'll be looking at today. And I believe that you can get those from PDH source. And that, again, is by going to the website, logging into your account, following the instructions, and with a little bit of luck, you should be able to download a copy of the PowerPoints. Okay, and then, of course, the last thing to put a little bit of emphasis on here, as far as the title of the webinar, is that we are talking about fire protection engineering for buildings. There, of course, are other fire protection situations that can be encountered, but we're talking about buildings and what you do in general in building design to address these fire protection concerns. Okay, let's see. What I will be talking about today is it's just kind of a smorgasbord of comments. And I'll explain why it's that way a little further on. But I'll be talking a little bit about building materials and design features that you incorporate into a building because of concerns about fires and life safety in the event of a fire. I'll also be talking about a topic that uh, generally speaking, engineers and architects don't aren't really cognizant of, and that's water supply for fire protection purposes. Because in most situations, you're designing a building in an urban environment. There's a water line out there in the street. You just hook up to it, and that's your supply of water for fire protection purposes. But it's not always that way. Particularly as an example, if you have a building in a remote location, there is no city water supply out there for you to hook up to. So you need to have a supply of water for fire protection purposes. And how big does that water supply need to be? What quantity of water do you have to have available for fire protection purposes for a building like yours? And we'll talk about that. We'll talk a little bit about, we will talk about fire extinguishing systems. Once you have a fire that starts, how do you put it out? Well, obviously, we all know you grab a garden hose and squirt some water on it. And water is, of course, the biggest, most significant way of extinguishing fires, but there are other ways to extinguish a fire. And in some cases, you don't want to use water on certain types of fires because they don't work. I'll talk a little bit about special occupancies and hazards. These are different kinds of buildings and occupancies of buildings, what's going on in the building, what kind of people are in the building, and how they are treated differently. And there are a whole slew of them that are defined in the appropriate fire codes. I'll just be talking briefly about some of the most common ones that you'll run into. And then storage of flammable and hazardous materials. This is the issue of fuels. To have a fire, you need fuel of some sort. So that's kind of what the chapters in the book, if you will, the way I'll be picking things up. Here, for introductory purposes, is a little bit about me and what I've been doing for the last few decades. For 35 years, I was what I characterize as a straight-ahead designer of buildings and related infrastructure, drawing specs. And I I got, let's see, I goofed up there. Okay, I got registered in a few different things along the way. I'm basically a mechanical engineer. That was my degree in my first registration. And along the way, I did get registered as a fire protection engineer. Couple comments there, just for your career development purposes or whatever. You might be thinking about, well, gee, I might like to get registered as a fire protection engineer. And the key to success in taking the fire protection engineer registration, in my experience, in my view, is simply making sure when you go into the exam that you have a little red wagon that's stacked with the fire codes because taking the exam, in my experience, was kind of just a matter of knowing which fire code to grab and to look up the answer. Fire protection engineering is almost totally code and regulation driven. That means with a given situation, as far as building design, you need to go to the right code and look up how you're supposed to do things. There's very, very little in the fire protection business that falls into, or is, you might call, sort of theoretical kind of stuff that you learn in engineering school in the first couple of years. Probably the only thing that of a, quote, theoretical, end quote, kind of nature that you'll run into is the flow of fluids in pipes, the hydraulics, calculating pressure loss, and that's when you are designing a water sprinkler system that is going to automatically extinguish fires in your building. And then you need to know a little bit about Bernoulli's equation and that sort of thing. But it's a pretty simple theoretical exercise, and there's a pretty easy way to do it. Otherwise, like I say, vast majority of fire protection engineering is driven by codes and regulations. You go and you read the right code. Now, as far as these marvelous codes are concerned, they are produced to a very large extent by NFPA, the National Fire Protection Association, and some others are produced by the International Code Council, and the the codes don't necessarily say the same thing about a given circumstance. So you need to make sure you know which codes the building department where your project is located rely on, and then you need to use those codes. Just from historical, semi-historical purposes or interest, NFPA was created in the last century primarily because of a disastrous fire that took place in a nightclub in the Boston, Massachusetts area. And there were a lot of fatalities. And the insurance industry, as a result of that fire, because back at that point in time, there really was nobody that was addressing fire protection issues from a technical standpoint. And the insurance industry kind of said, well, we need to have an organization to address fire protection issues in buildings. So we'll create one. We'll call it the National Fire Protection Association. And that's what we have today. And it is the primary producer of codes and regulations in this area. The building codes, originally the uniform building codes, and then that got transmogrified into the International Building Council. It also produces some codes in the fire protection area. They don't always agree 100% with the NFPA codes, so you need to watch out for that. When the International Code Council was created, historically, because I was kind of around at that time, there was an effort that was made to get the NFPA to cooperate and become part of the International Code Council, along with all of the other engineering societies, ASCE, ASME, et cetera, et cetera, et cetera. But NFPA elected not to, shall we say, integrate its activities with the Code Council. So you get some kind of differences there between the two. Okay, anyway, this is what I've been doing, and 35 years as I say, as a straight ahead building design and infrastructure designer. I have not spent 35 years doing nothing but fire protection engineering. It's just been an adjunct of the building and infrastructure design that I've been doing. So here's kind of very quickly the points I'll touch on, the principles of fire protection engineering that affect the building materials and design. And this is where things begin to get real, if you will, as far as what most of us in this field are doing. And that is the selection of the right building materials and incorporating the right design features into a building because of the particular threat that fire presents. The adequacy of the water supply, fire extinguishing systems. I'll have a few comments on the different types of fire alarm systems. These are the systems that detect a fire, that report the fire, typically to the local fire department, and sound a local alarm that tells people to get out of the building. Become familiar with the requirements of special hazards and occupancies. Special hazards is your building. Are you storing a lot of flammable fluids or other materials in the building, et cetera, et cetera, et cetera? Are there some kind of industrial processes going on that increase the risk of fire? And then the occupancies, in other words, the people in the building. Is everybody that's in there fully mobile, able to get around, able to see? You don't have to be concerned about blind occupants, but maybe that possibility may exist, and other kinds of handicaps. Okay, so this is how I'll run through things, the elements of fire protection engineering. The hazard classification system, the hazards have for different hazards in a building, there are different things that are required, like fire areas. There'll be more about this as we move along. Height limitations, maybe that because of the nature of the building and the occupancies, there is a limit on on its height, or perhaps the height of stored materials in the building, like in a warehouse. Interior fire spread. This is a fundamental concept to keep in mind in fire protection engineering for buildings, is to prevent the spread of fire from where it breaks out in the building to other parts of the building, and to retard the spread of fire within a building for an appropriate period of time to allow the occupants to get out of the building safely. Because the objective of fire protection engineering is not to keep the building from burning down, to prevent loss of property. That's nice as far as fire protection engineering is concerned, if you can limit the damage to the building. But the key objective of fire protection engineering is life safety. Get the people out of the building, and then if the building burns down, why, you know, that's the insurance company's problem. Egress, in other words, and getting people out of the building, in general, that's termed egress, which means how people get out of the building. In simplified form, what this usually means is corridors and stairwells. That's how people get out of the building. Interior finishes, wall coverings, carpet, ceiling materials, etc., etc. The key concept here is that interior finishes potentially serve as fuel for a fire. They burn. And you don't want those interior finishes, the carpet, the wall coverings, etc., to be burning. The more impaired your occupancy, your people are, the more attention you need to pay to interior finishes that do not provide fuel for the fire. Because the impaired occupants, it takes them more time to get out of the building. Insulation is a material, an example of a material that in the olden days, the original or the early insulation materials that were used in building design and construction were flammable, and this posed a risk. And so now insulation materials that are now on the market need to adhere by code and regulation to certain levels of being inflammable or slow burning and smoke development. This is a point that has over the years become more and more apparent, is that in the case of a fire, as far as life safety is concerned, smoke development is probably even more of a threat to occupants, to people, than are the flames. And so there is emphasis in current regulations and standards and this sort of thing on limited smoke development as far as a particular product is concerned. You don't want one that creates a lot of smoke. Roof coverings is very important in building design from a fire protection purposes. These days, that the heat vector, you might say, of a fire is vertically. You have a fire, and you know this from observing fires. It points upward, and that's where it's hottest. And so you get a fire started in a building, a very high intensity of heat is exposed to the, or is targeted at the roof. And so the roof is one of the weak points in a building. And it is a significant threat or hazard, because once the roof fails and the fire bursts out of the top of the building, thermal drafts are created. Very high intensity drafts that shoot the flames way up in the air. They blow burning debris out the top of the building. And this stuff poses a threat to nearby buildings. And so the maintaining the integrity of the roof structure and covering is an important objective of building design. And this, as an example, one of the first things that you see when a fire breaks out in a building typically is the fire department arrives, and some of the firefighters, rather than heading for wherever the fire is in the building, they head for the roof of the building and they start squirting water all over the place to keep the roof cooled down, to keep the roof from the fire from breaking out through the roof. This breaking out of the fire through the roof was kind of brought home to the fire protection engineering community with the famous Chicago fire that started in Mrs. O'Leary's barn, and fire broke out from the roof, and burning debris was blown all over the place, other buildings caught on fire, et cetera, et cetera. So roof coverings, very important consideration in building design. Another important consideration in building design is roof and fire department access. And this is for purposes of extinguishing the fire. Now, there are two ways, fundamental ways, that a fire gets extinguished. There may be an automatic fire extinguishing system in the building. Now, in the vast majority of buildings, this is going to be a water sprinkler system. And when a fire breaks out, the sensors and the controls automatically release water onto the fire, and that is done to extinguish the fire. And so automatic extinguishing systems, like a water extinguishing system, or there are other extinguishing systems in more specialized spaces. And then the second category of mechanisms for extinguishing a fire is the fire department when they arrive at your building, and with their hoses and the water. Important considerations here in building design and in siting the building are access for the fire department firemen to get to the roof of the building and to get to spaces in the building where the fire may have broken out. So getting access for the firefighters to the fire, that means, for one thing, it means there needs to be an unobstructed path to get a fire truck to a position adjacent to the building such that it can do what it needs to do. A common example is a positioning of a pumper truck in the event of a fire. Let's say you're in an urban environment, you've got a municipal water system out in the street, and you've got fire plugs out there. And so you drive up, the fire department drives a pumper truck up to the side of the building. They connect a hose to the fire hydrant in the street. They connect the other end of that hose to a pump in the pumper truck. And then there is another hose that typically, and I'm kind of describing a multi-story building now, there is a connection typically on the outside of the building where the fire department connects a hose to the output of its pump on its pumper truck. The other end is connected to a fire department access fitting on the outside of the building, and that fitting is connected to typically a vertical pipe that it runs the full height of the building. Again, I'm talking about a generic multi-story building fire. And this vertical pipe, a fire department riser, a fire riser, at each floor there is a T and a valve and a fitting so that the firefighters can connect their fire hoses at, say, the 5th floor to the T-fitting in the stairwell typically, and then connect their hose and then go and fight the fire on the 5th floor or the 6th floor or wherever it happens to be. And then the pumper truck is down on the ground and the pump is turned on, and that increases the pressure in the risers so that the water will go all the way to the top of the building. And because the pressure for typical municipal water systems will only get the water up to around the 10th floor in a multi-story building. Above that, you need to increase the pressure using a pumper truck. And so the firefighters have to have all of this access for their truck, and then they need to be able to get access to where the fire is burning in the building on the 5th floor or the 6th floor. They need to get access to the roof to keep it cool. As far as vertical access is concerned, usually this is a stairwell, which is constructed of a highly fire-resistant type of material, like poured in place concrete or concrete masonry or CMU blocks, something like that, so that that stairwell, its integrity, structural integrity, is maintained all of the time that the fire is being fought. And this stairwell serves not only for providing fire department access to where the fire is and to the roof, but it also is an egress route for the people in the building to get out of the building. Fundamentally, the egress routes are stairwells and corridors. And it's important that they maintain their structural integrity long enough to allow the people to get out of the building. Now, another important consideration as far as building materials and design is the air handling system, the air conditioning system. You got a fan blowing air all over the building, and it has been recognized in recent decades that the air handling system is a significant concern in the event a fire breaks out in the building, because it breaks out, say, in one location and there's a lot of smoke being developed and the air conditioning system is sucking this smoke out of the place where the fire started and blowing it all over the building and creating a hazard for people in other parts of the building other than where the fire actually broke out. And and to a lesser degree, the duct system can transmit the fire itself, flames. This occurs typically if you've got some flammable materials in the air distribution system. And so current contemporary design of HVAC systems requires that, first of all, you keep flammable materials out of the air distribution system. Secondly, that you have a control system so that when a fire breaks out somewhere in the building, you automatically shut off the air conditioning system so that it is not forcing smoke around the building. And it, in a larger, more sophisticated contemporary building, the controls on the air handling system might, as an example, shut off the the primary air moving fan in the system, and through a system of dampers and controls, perhaps a second fan will come on, or maybe the primary air moving fan will remain functioning, but the air will, from where the fire breaks out, is exhausted directly to the exterior of the building. And that helps to prevent it from the smoke from spreading to other parts of the building. And so that type of controls is kind of the standard on HVAC systems these days. Shut the primary air handling, air moving fan off, and then perhaps maybe using a second fan and controls and dampers and this sort of thing, exhaust the air where the fire has broken out directly to the exterior. And that it helps substantially to mitigate the smoke in other parts of the building. And as far as the fire spreading through the air handling system, the key here is to avoid having flammable materials in the air handling system. Like, as an example, in a lot of office buildings, the air conditioning system pushes air into the occupied space. There is not a ducted return in many designs, but rather the plenum space, the space between the suspended ceiling and the deck above, is used as a big return duct for the air handling system. And of course, that space also can be used for conduits and ducts and things like that. But since this is now part of the air handling system, all of those kinds of things that you might put in the plenum space above the ceiling, like pipes and conduits, needs to be of non-flammable materials. So no plastic, that sort of thing. Same thing with the electrical distribution system. The insulation needs to be non-flammable. Okay. Now we'll talk about the water supply system, and essentially water supply. How much water do you need to put out a fire in your building? There is a methodology that I'll show you for calculating the demand for a sprinklered facility, one that has an automatic sprinkler system, and then demand for an unsprinklered facility, one that does not have a conventional fire sprinkler system. More and more the codes are mandating that buildings above a certain limited size have automatic sprinkler systems in them, but there still are buildings out there that are not required by code or regulation to have a automatic sprinkler system in there. Okay, and the fire extinguishing systems, the most common is the water sprinkling system, water sprinklers. That's the automatic sprinkler system, but there are others that are used in different situations. There are foam systems, AFFF, aqueous foam forming film systems, dry chemical systems, carbon dioxide systems, clean agent systems that were the original one was called Halon 1301. And they are used in with different hazards in buildings. The alarm system, fundamentally what it does is it detects a fire, it reports the fire typically to the fire department, but it may also report it, say, to a facilities manager at a college campus or something like that. And then the local alarm system that sounds and tells people to get out of the building. The special occupancies and hazards, there are many, many, many of them that are defined in the codes. Many of them you'll never encounter in a typical career. Ones where you will be more likely to encounter special requirements are food preparation areas, kitchens, that sort of thing, medical facilities, hospitals, clinics, that sort of thing. The key driver here is the impaired populations, the patients that you have, and they cannot move around as readily as fully capable people can. Food preparation, the issue there is that certain types of fires, like grease fires, cannot be extinguished by using water. And the reason is that grease, as an example, is lighter than water. So if you spray water on top of a grease fire, the grease just floats on top and keeps burning, and you can't put the fire out. Detention facilities, jails, prisons, etc., etc. The challenge here is similar to that in medical facilities, in that you have, you might say, an impaired population themselves, and you don't want those folks in the event of a fire. You don't want those folks in the event of a fire running out the front door and getting away, that sort of thing. Electronics and telecommunications facilities, this has been a relatively recent situation to deal with since the computer age has come upon us in the last few decades. The issue here is that you have a computer room with a lot of expensive computer or electronic or electrical equipment in it, and you get a little fire that starts in a wastebasket. You don't want to open up a whole bunch of water sprinklers and spray them all over all of this expensive equipment because it ruins the expensive equipment and may ruin a lot of very important data. And so there are special ways of having to challenges in extinguishing fires in these kinds of facilities. The high-rise buildings, the issue there is firefighter access to the where the fire is, and then egress for the occupants, the corridors and the stairwells. Okay, codes and other professional resources. At the end of these slides, I included several slides which contain nothing but an enumeration or listing of some of the zillions of codes, most of them NFPA codes, that are applicable in fire protection engineering. And I did this just to get across to you how completely code and regulation driven the fire protection engineering business is. Up until the last few decades, fire protection was not a major area of emphasis for plan checking departments, the building departments, when you submitted a set of plans for a building. They tended to focus more on structural safety and maybe a few other things. But now fire and life safety is right up there with structural safety as far as concerns for the plan checking community, building departments. So Okay, let me see. I'm looking at my clock here. We're getting close. Oh, another point to keep in mind when you have a building and you're submitting it for plan check to the building department, bear in mind that in addition to your plans being reviewed by the building department, where generally speaking, the reviewers are going to be professional engineers, perhaps more junior, and possibly even just engineering technicians. But in any event, the plans are going to be checked by people with a pretty good skill level and knowledge as far as building design and construction is concerned. But in addition to the building department, your plans typically are going to be checked by the fire department. And with the fire department, no fire departments have technically competent, if you will, people. They have firefighters and they give them a little bit of training in plan checking, but it's kind of a community of plan checkers that doesn't have a high level of technical expertise. The point here is that you need to use your diplomatic skills in the preparation of your drawings and specs and make sure that everything is crystal clear to the fire department plan checkers what your thought process was in developing your design so that you guide them in a diplomatic way through the review of your plans, because if they don't approve the plans, they're not going anywhere. And the key element there is a design analysis, which I'll show you a typical outline for one shortly. This is kind of the table of contents, if you will, that guides the plan checkers, not only in the building department, but importantly in the fire department in reviewing your plans. Now, a final point here, everything that I'm telling you today is strictly for illustration purposes. In all instances, do not refer to these slides or anything you hear or see here in the design of a particular building that you're working on. You need to be guided by the actual codes and regulations that apply. So just a little caveat there. So let me see, my time is where we're almost ready to take our first 10-minute break. You've got a building, you're designing the fire protection system. The first step is to produce and be guided by a design analysis with a certain kind of format, because it helps to shape your thinking, and it then serves as a table of contents, if you will, for the plan checkers in the building department and in the fire department. And this is a typical table of contents, if you will, for design analysis. Building code analysis. What code are you using? Tell the reviewers. And what is the type of construction as defined by that code? You're building the building out of concrete, steel, wood, hay bales. And so you tell them what the type is as defined by the applicable building code, and any height and area limitations, building separations, or exposure protection. This is addressing the point of a fire breaks out in your building, and how far is it to nearby buildings? If these nearby buildings are very close to your building or right up against your building in an urban environment, then those buildings are threatened by the fire in your building, and you have to do certain things to protect those other buildings, like the fire resistive construction of the separation wall between your building and the building next door, the continuing the exterior walls vertically above the roof for a certain distance, 4 feet, 6 feet, something like that, to prevent, in the event of a fire breaking out of the roof, burning debris, being blown over onto adjacent buildings. What's the classification of the occupancy, the people that are going to be in your building? Are they standard variety office workers? But of course, among that office worker community can be people with handicaps. And so you have to classify the people, the occupancy. And of course, then you have medical facilities, detention facilities, et cetera, et cetera. Code requirements for fire rated walls, doors, dampers, et cetera, all of these as dictated by the applicable code. The NFPA 101, the life safety code, there's a lot of kind of overlap here with the typical fire codes, but in essence, the life safety code, NFPA 101, is directed at the occupants of the building and making them aware that a fire is broken out and getting them out of the building expeditiously. And so on and on through these additional points here. This is the table of contents, if you will, for your drawings and specs, and it guides your thinking in the design process, and then it serves, as I say, as a table of contents for the plan reviewers. Okay, let's pause here and take a 10-minute break. I've got 8 minutes before the hour. Let's take a 10-minute break and come back at 2 minutes after the hour, and we'll pick up here and press on. So I'll see you all in 10 minutes. Okay, this is Paul Geyer, and I'm back, and we'll press on here. Now, occupancy hazard classification system. This is defined by whatever code you're using, NFPA codes, International Code Council codes. Um, and every time they come out with a new version of the codes, they like to change the nomenclature. Essentially, though, defining the occupancy hazard ranges from not so hazardous to really hazardous. And this is the nomenclature that is used in one area, and it's the one that I use here on these slides. Light hazard occupancies, it's not much, hazard to the occupants because of the nature of their activities or the construction of the building. Ordinary hazard group 1, a little more hazardous, ordinary hazard group 2, more hazardous, and then special occupancies are significantly hazardous occupancies. And the light hazard occupancies, as the term is used here, would typically be just run-of-the-mill offices, child development centers, a lot of little kids, places of limited assembly, churches, so on and so forth. Ordinary hazard group 1, more hazardous, kitchens and bakeries, sheet metal shops, laundries, parking garages, theaters, auditoriums, because you've got more hazardous activities going on in these occupancies, or the materials or stuff that's being used is more hazardous. It's flammable, that sort of thing. Ordinary hazard group 2, even more hazardous, things like department stores, supermarkets, and so on and so forth. And you might be asking the question, well, why are department stores and supermarkets so hazardous? Well, it's because they have so much stuff in them that is potentially fuel for a fire. So that's an important point to keep in mind, the quantity of fuel in your building. Electrical maintenance shops, labs, switchgear rooms, et cetera, there the hazard is the electrical system, electrical distribution system. It poses threats, hazards. And the most hazardous occupancies, special occupancies, an example is warehouses. Now, again, you might say, well, what's the big problem with warehouses? But again, it's because of all of that stuff or fuel that is stored in these buildings. And it's stacked to the ceiling, etc. So it's got a lot of fuel. Aircraft hangars, of course, you got airplanes that are full of fuel, big hazard, et cetera, et cetera. So let's press on here and get through the some of the points as far as the building materials and designs. A fundamental point in fire protection engineering, as I said earlier, is to protect the occupants of the building. A fire breaks out in a location in the building and you want to prevent that fire from spreading rapidly to other parts of the building so as to give the occupants of the building time to get out of the building. And the way you do that, basically, or a very important way that you prevent the spread of fire, is by the construction as part of your building design of partitions, that is walls, ceilings, floors. And so the codes will mandate that the partition between this kind of activity or occupancy and the adjacent occupancy, the partition, the wall between the two, needs to be of a certain fire resistive construction. 1 hour fire resistance, 2 hour fire resistance, etc. How are these fire resistance ratings determined? They're determined by test. The commercial interests in the building materials business, the gypboard people, the steel stud people, et cetera, they want to be able to market their products, their materials, and to be able to say to the engineers and architects that are designing these buildings, well, if you design the partition this way, 6-inch steel studs at 16 on center with 5/8 chipboard each side, that it will have a fire resistive construction of 1 hour or 2 hours or 3 hours. And so the commercial interests then go to an independent testing laboratory. In many cases, it's underwriters' laboratories that do the testing. And underwriters' laboratories just constructs a test panel and subjects it to a fire in a lab or field setting, and makes a determination using its methodology. And its methodology has probably been memorialized in as an ASTM testing standard. So it uses an ASTM standard for testing the fire resistive characteristics of this particular wall construction. And using that ASTM methodology, it makes a determination that this construction, that a fire resistive rating of 1 hour or 2 hours or whatever is appropriate. And so then the gypboard people just in their catalog material, they just say, okay, if you construct your barrier, your walls this way, it will have a 1 hour fire resistive construction. And the fire resistivity of the construction of barriers, the walls, floors, is very important with regard to the egress routes, the corridors and the stairwells, because for life safety purposes, you want those features of a building to maintain their integrity for as long as practicable, to allow the people as much time as possible to get out of the building. And so that's essentially what you're doing with the design of your partitions in a building, the walls, ceilings, floors. The separation between buildings, this again is driven by codes. And so if you the nearest building is so far away from you, then you need to have exterior walls and roof constructed of such and such structural system and coverings. And the closer those nearby buildings get to your building, why the greater the fire resistivity of your exterior walls and roof needs to be. The fire area, we'll come to that in a moment. a point to keep in mind as far as these partitions in your building are concerned, walls, ceilings, floors, is that if a partition between one area of occupancy and another area of occupancy is specified by code to be 1 hour fire resistive construction, 2 hour, 4 hour, whatever, that that means everything in that wall needs to be of that fire resistive construction. So that means doors, window assemblies, and things like that. And this includes things like, in particular, the HVAC system, the ducts, as they pass from one occupancy to another. If the barrier, the partition between the one occupancy and another occupancy is required to be of 2 hour fire resistive construction, then there needs to be a fire resistive barrier incorporated into the ductwork system and the air conditioning system. And this is typically a damper, an automatic damper. So in the event of a fire, it might be a fusible link damper, fusible link melts, damper drops, and the damper has a 2 hour fire resistive construction, which prevents the spread of flame and also smoke from one area to another. And also there are electronic releases on fire doors as well, rather than fusible link. And there may be rolling or sliding doors, things like that. You go on a ship, a cruise ship, something like that. There are automatic fire doors that, in the event of a fire in one part of the ship, these doors automatically close. And so these duct penetrations are important. The means of egress, an important consideration as far as the egress routes. Fire alarm goes off, people hear it, how do they, what are they supposed to do? Well, they have to be guided by signs, typically, that say exit, you know, this way, or this door, you know, is to be opened only in the case of fire, something like that. And that's how people get out of the building, as they see these signs. Now, these signs, over decades, the last few decades, they have become more broadly usable by impaired populations. And so, as an example, well, for one thing, they're illuminated. So, and they have a battery pack in them so that in the event of a fire and the electrical system goes out, these signs that say exit this way are illuminated, and people can see that in the dark and can leave. But then you also have to consider the possibility that there may be blind or deaf people in the building, and so these exit signals, exit signs, now incorporate audible signals so that a blind person can hear the horn, and or it might even be a recorded message that says something about move forward, turn left, move forward, turn left, something like that. And then the deaf, these signals now incorporate typically strobe lights, so that a deaf person is working at his desk and suddenly a strobe light goes off and he knows something's wrong and that he needs to get out of the building. So these are the methodologies that are used today with these exit route, egress route indicators, signs, illuminated, audible alarms, visual alarms, and that's important in getting the people out of the building safely. The interior finishes I touched on already. The importance of interior finishes, the important point is that they provide fuel. And this is particularly important, as an example, in hospitals and medical clinics, things like this, where you have people who quite simply are bedridden, cannot move around easily, and so you want to keep them as safe as possible in place. So you don't want the carpet to burn, you don't want the wall coverings to burn, et cetera, et cetera. And the a concept in medical facilities and others when you have these significantly impaired populations is the area of refuge concept. In other words, this is a space, typically we'll say, in a hospital on one floor, and what is called an area of refuge is constructed. Typically, this is the elevator lobby on the floor. And this is constructed by installing automatic fire doors that close automatically in the event of a fire. And they can be opened by nurses and medical personnel, of course. But the impaired population, and these fire doors are of a high level of fire resistive construction. And so the impaired patients are moved into this area of refuge, and the fire doors are closed, and they are in a protected environment while the fire is being extinguished. And of course, this also gets them out of the way of the firefighters so that the firefighters can do what they need to do. So areas of refuge is an important concept with impaired populations. And this could be employed in a detention facility. In the event of a fire, you get all of the prisoners to move to an area of refuge, and then they can do whatever they do in a group setting like that. Okay, interior finishes, the roof covering and the roof deck assemblies. I pointed out the the importance of the roof structure and the roof coverings. The point being the objective to keep the fire from breaking out of the roof, because then burning debris poses a hazard to nearby buildings. The fire department access, to be able to get the truck to the side of the building, and then to be able to get the firefighters in a generic multi-story building up to the floor where the fire is, and they can connect their hoses to the fire riser, and then they can get up to the roof of the building and keep it wetted down. And the air handling systems, we touched on that. There's a lot of discussion in these slides that we don't have time to get into in detail, so I'm going to be kind of speeding through them. The air handling system, an important consideration in building design from the fire protection purpose. And again, to reemphasize that more and more has come to be an appreciation of the fact that smoke is in a lot of cases more hazardous to the occupants than are the flames. Okay, now that was just a quick walkthrough of the building materials and design features and things to think about. Conceptually, you're building barriers, walls, ceilings, floors to prevent the spread of the fire to other parts of the building, and that maintaining the integrity of the egress routes, the corridors, the stairwells, is very important, because those are the egress routes people use to get out of the building, and they are the access routes that the firefighters use when they show up to fight the fire. Okay, now let's look at this issue of water supply. You're building a building and you need fire protection for it, and you have got construction 95% done, and you walk out to the road and start looking for the fire hydrant, and there's no fire hydrant. And as a matter of fact, there's no water distribution system. In other words, you've got a building in a remote location. There is no municipal water supply present there. So how much water do you need, and how do you get it if you don't have a municipal water system? Well, very simply, if you don't have a municipal water system to hook up to, you have to store water on site for fire protection purposes. And a place where you run into this, even in an urban environment, quite regularly, is in warehouses, because they have so much fuel in them. They are a significant fire risk, and they're big often. And so the, the municipal water system isn't adequate to serve them. And so they have, when you drive into a business, a commercial park, an industrial park, a lot of warehouses, you may well see some big tanks sitting outside of these buildings. They may be concealed by architectural features, but those are water tanks where the water for fire protection purposes is being stored. But how big does that tank need to be? How much water do you need to have? Well, here is a methodology that has been developed and has been used for many, many decades, and has proven to be practicable. It is a simple system, easy to use, but don't, because of its simplicity, feel that it's inadequate. And this system is the one that has been developed and is used by the Department of Defense, primarily the Army Corps of Engineers and the Naval Facilities Engineering Command. There's nothing governmental or bureaucratic or Army, Navy, or anything like that about this. It's just good, solid engineering logic. And so for a sprinklered facility, a facility that typically by code you are required to have an automatic sprinkler system, there are two requirements, two things that require water. One is the automatic sprinkler system, and the other is the hose stream. This is the water you make available for the firefighters to use when they show up. And the sum of those two is the total water demand. And is this system. Again, it's been used for decades and decades and decades, and has been proven to be quite practicable. So you've got the occupancy classification, whatever it might be called, in the column on the left, ranging at the top, excuse me, from the light hazard occupancies down to the most hazardous. So for the automatic sprinkler system, this methodology says you need to have a design water density as indicated in the second column from the left, gallons per minute per square foot of fire area. So for a light hazard occupancy, run-of-the-mill office occupancy, 0.1 gallons per minute per square foot of fire area is the quantity of water that you need to deliver to a fire that breaks out in that area. Now, what is the design area? This is an assumption that you are making of what the area is of the fire. And it is 3,000 square feet. And there's no way you can calculate this on any kind of a theoretical basis. It's just been tried and modified and used for decades and decades, and it is practicable. So the assumption is that a fire of 3,000 square foot area has broken out in your building. The occupancy is light hazard. The density of water that you need to deliver to that fire is the 0.1 GPM per square foot, or for the 3,000 square foot design area, that means you need to deliver 300 gallons per minute of water to that fire. So that's for the automatic sprinkler system, water needed for the automatic sprinkler system. Then there is the hose stream allowance. This is the water that needs to be available for the use of the firemen when they show up, and it is 250 GPM. And in this system, there's no way to calculate that. Theoretically, it's just a number that has been tried and used and has demonstrated its practicability over a long period of time. So you need then, for a light hazard occupancy, 300 GPM of water is required, plus 250 GPM, or 500, a total of 550 gallons per minute of water needs to be delivered to the fire. And for what duration does this supply need to be provided? This is the assumption that is made that you will extinguish that fire within this period of time. And that duration of supply is 60 minutes for a light hazard occupancy. So 300 GPM plus 250 GPM gives 550 GPM for 60 minutes. So that means that you need 33,000 gallons of water for fire protection purposes. So if you didn't have a municipal water system, you would build a tank and of that size, and that would be your fire protection water. Also, this type of a calculation, if you are in an area that has a municipal water system, this type of a calculation is done either by you or by the water department. And then the water department uses its methodologies to decide if it can reasonably supply that quantity of water over that period of time. And if the municipal water utility gets back to you and says, yeah, we can supply that quantity of water to you for fire protection purposes, then fine. Then you just rely on hooking up to the water system out in the street. But if the water utility gets back to you and says, no, we don't have the capacity to provide that quantity of water to you for fire protection purposes, and so you're going to have to store water on site. And so down through all of the increasingly more hazardous occupancies, until you get down to the bottom in this characterization, extra hazard group 2 occupancies, the most hazardous occupancies. The design density for the automatic sprinkler system is 0.4 GPM per square foot. And you will notice that the design area of fire it's still 3,000 square feet. And this may seem a little counterintuitive that the design area of the fire remains the same from light hazard through to the most hazardous occupancies. It's still 3,000 square feet. And this, as I say, may seem a little counterintuitive to you, but actually it isn't, because the thinking is that by putting the higher density of water on the fires in the more hazardous occupancies, you're still going to contain the fire to this 3,000 square foot area. So that's why the design area of the fire does not change. The hose stream requirement does increase with the hazardous nature of the occupancy. So down at the most hazardous occupancy in this system, extra hazard group 2, you would need 1,200 GPM for the automatic sprinkler system, and 750 GPM for the hose stream. That's 1950 gallons per minute. For the more hazardous occupancies, this water needs to be available for 120 minutes. And so for the extra hazard group 2 occupancy, the volume of water that's needed is 234,000 gallons. So that's how big you need to make the tank if you have to store water on site. So this is a methodology for determining how much water you need for your building for fire protection purposes if your building is mandated by code to be served by an automatic sprinkler system. For an unsprinkled building, and these tend to be the smaller, less significant buildings, the methodology used by, again, the Department of Defense is different, still simple, and it involves a consideration of certain factors. The occupancy classification, response time by the fire department, because the fire department is the only method that you've got available, absent a fire sprinkler system, to put out the fire. The type of construction, is your building made out of wood, concrete, steel? Number of stories, separation distance to other buildings, and building floor area, and then firefighting access. And this methodology is a simple point system that goes like this. Response time by the fire department. If the fire station is less than 2 miles away, your building in this point system gets 2 points. If it's more than 2 miles away, it gets 3 points. And you can come up with all sorts of things to speculate about. The bottom line is that this system has proven to be practicable. what is the type of construction? And the types of construction are defined by code and range from the most vulnerable type of a building, like a wood building, to the least vulnerable type would be a concrete building. And the points that are awarded based on the type of construction of your building range from 1 to 5. Least hazardous construction, your building gets 1 point. Most hazardous construction gets 5 points. No rational theoretical way to go about calculating this. It's just been done, tried, trial and error, and it works. Number of stories in your building: 1 story, 1 point; 2 or more stories, 2 points. And it doesn't matter if your building is 20 stories or 40 stories, it still gets only 2 points. It's counterintuitive, but it works. Building floor area, 7,500 square feet or less, your building gets 1 point. On up to greater than 40,000 square feet, gets 5 points. If your building is 200,000 square feet, doesn't make any difference. It still gets only 5 points. Let me get back to the slide that got away from me. It still gets just 5 points. The separation distance to nearby buildings, more than 60 feet, your building gets 1 point. 21 to 59, 2 points. Less than 20 feet, 4 points. Maximum hose layout. This is from the fire plug in the street to the pumper truck, from the pumper truck to wherever the fire is in the building, up to a maximum of 3 stories high. If that hose layout is 180 feet or less, 1 point. 181 to 230 feet, 2 points. More than 230 feet, 4 points. And so your building has been awarded points based on all of these different criteria. And you then go to this table here: water demand for unsprinkled facilities. The occupancy hazard is in the column on the left. If your building got 6 to 10 points, the fire flow requirement, GPM, if it is a light hazard occupancy, the fire flow requirement is 750 GPM. For an extra hazard occupancy, the same number of points, 6 to 10, the fire flow requirement is 2,500 GPM. If your building gets over 16 points, light hazard occupancy, 1,500 GPM is required. And for extra hazard, more than 16 points, 5,000 GPM. And then the duration for which that flow rate, GPM, is required is as indicated in the last 3 columns on the right. Light hazard occupancy, 6 to 10 points, 60 minutes. So 60 minutes times 750. So the total quantity of water is 45,000 gallons. Light hazard occupancy greater than 16 points, 1,500 GPM times 120 minutes. The volume of water required to be available is 180,000 gallons. And so on through the table. So that's how much water you need to have available. If your local water utility can supply it, they'll get back to you and say, yeah, we can supply that. Or Uh, if there is no local water utility, or if the water utility gets back to you and says, no, we can't supply that quantity of water, then you need to store it on site. Sometimes, parenthetically, if you have a remote building, like a building out in the woods somewhere, no water utility, but maybe there's a stream running by. And so it is not unreasonable to consider a stream as a source of water. And so you construct some kind of a Rube Goldberg intake structure, and you just take water out of the stream for your water supply. Or you might have to use groundwater. That gets into the reliability of the pumping system, but anyway. So now just for illustration purposes, again, this is a methodology used by the Department of Defense for non-building, and a type of non-building fire hazard, like a fuel farm, petroleum oil lubricant storage. And you've got a bunch of these big storage tanks. This is the methodology that DoD uses. And it's based simply on the diameter of the tank. Get my slide back here. On the diameter of the tank. So if the diameter of the fuel storage tank is less than 64 inches, the fire flow rate required is 500 GPM. No way to calculate that theoretically. That's just what has worked. And the duration that is required for that flow rate is 240 minutes. So 500 times 240 minutes, that's 120,000 gallons of water is required, and so on through the table. Now, you might be asking, well, this system is based on the diameter of the fuel tank, but what about the height or depth of the fuel tank? You could have a 64-inch diameter fuel tank that's 1 inch high or 50 feet high. The point here with fuel storage tanks is that the fuel is lighter than the water, and the only thing that is burning is the top layer of the fuel in the fuel tank. So it's irrelevant how much fuel there is down in the tank below the top surface. It's that top surface area that is the threat, if you will. And here is just another illustration of the same methodology for multiple tanks, a tank farm or a refinery type location, something like that. So this is just for illustration. Okay, we've just got a few minutes left, so I want to touch on the one thing that you will potentially have occasion to do with fire protection systems in buildings, and that is sizing the pipes in the fire sprinkler system. The fire extinguishing systems, real quickly, the big system here, of course, is the automatic water sprinkler systems. The foam, they are similar to a water sprinkler system, except what they do is they mix water with a chemical and then spray that chemical out of these sprinkler heads, these fire heads, and it forms a foam of bubbles that floats on top of the burning fuel fire, like in an aircraft hangar, and it smothers the fire. Dry chemical systems, this is applicable to often to food service facilities, kitchens, this sort of thing. A place where fires frequently break out in food service or kitchen areas is over the cooking surfaces. You've got the exhaust fan sucking those greasy fumes out, and the grease accumulates in the exhaust system, catches on fire, and water is not something you can use to extinguish a grease fire. So dry chemicals of one form or another are automatically released into the duct system and the cooking surface to smother the fire. Carbon dioxide systems are frequently used for electrical fires in transformer vaults and electrical rooms and things like that, because water will not put out an electrical fire. But the carbon dioxide systems do it by depriving the fire of oxygen. So it puts the fire out that way. The carbon dioxide systems cannot be used in locations where there are normally people present, for the simple reason that if you remove the oxygen from the atmosphere, then the people are at risk. And then the Halon 1301 is another gas type system, originally developed a few decades ago to protect computer rooms, electronics equipment rooms, things like that, where you have high value equipment and high value data, and you don't want to have an automatic water sprinkler system go on and spray water all over this expensive equipment and ruin it and ruin the data. So Halon gas systems were developed, and they remove enough oxygen from the environment to suffocate the fire, but they do not remove so much that they present a hazard to the people that are in the area. So the people have time to get out with Halon 1301. Now, Halon 1301 has been identified as being an environmental hazard, and so those systems are being phased out and replaced with newer, all similar chemical gas systems called clean agent systems, and that's what's used in computer rooms and that sort of thing these days. Just a couple of minutes left. The automatic sprinkler system and sizing the pipes. And here's the way it goes here. You've got water being delivered to your building from the local water utility at around 50 psi. So that's the pressure at where the water enters the building. And at the most hydraulically remote location where a fire might break out, that's you need to calculate the pressure loss between where the water enters the building and that most hydraulically remote location, which is normally the most geographically remote. And so the way you go about it, and well, the fire sprinkler heads, you go to the catalog for fire sprinkler heads, and they'll typically say, if you supply water at, say, 20 psi to this head, it will deliver so many GPM per square foot over such and such an area. And so that tells you the quantity of water that needs to be discharged by that head when it has 20 psi available. So the pressure loss that you can take in your piping system between the point where the water enters the building and where it is discharged from the sprinkler head is 50 minus 20 or 30 psi. And the way you calculate your pressure loss is you you lay out your piping system, which is, you know, kind of a logical thing you simply do graphically. And then you make some assumptions about the sizes of pipes that you're going to need. And once you've done a few of these, well, you know pretty well what sizes they're going to be. The largest size in typical, many typical buildings is going to be around 2, maybe 2.5 inch diameter pipe where the water enters the building. And then as it travels to that most hydraulically remote location, there are tees off, and some of the water goes over here, some over there. And so out there at the far end, you have the GPM in that last pipe, and it's whatever you need. It's so many GPM over an area of 200 square feet. And that's the flow you need out of that head. And it needs to be delivered, that flow needs to be delivered to that head at 20, not less than 20 psi. So you lay out just by the seat of the pants your system. 2-inch pipe reduces down to 1.5, and then to 1 inch, and finally at maybe at 3/4 inch at that last pipe. And you've got these, each length of pipe has a length, and you know what that is, and you convert all of the fittings, the angles and the tees and things like that, into equivalent linear feet of pipe. So all of the 1 inch 90-degree elbows in that length of pipe are the equivalent for a 1 inch pipe of 5.2 linear feet of straight pipe. And so you just convert all of your piping to equivalent linear feet of straight pipe, so many linear feet, equivalent linear feet of 3/4 inch pipe, so many equivalent linear feet of 1 inch pipe, etc., etc., etc. And then you go to a table like this, commonly found in plumbing codes, and it gives you the flow rate versus the pressure drop per 100 feet, and for the different sizes of pipe. And so using a table like this, you determine the pressure loss in your piping. And if it turns out that you've got too much pressure loss and the pressure out there at the end of the pipe isn't the required 20 psi, it's only 15 psi, then you've got to go back and increase the size of some of your pipes from 1 inch to 1.25 or 1.5, etc., etc. Okay, that was a quickie on that. And this brings us to the end of our available time. This has been a very quick look at the